Hello everyone, in this lesson we are going to calculate support reaction for indeterminate beam, and we are going to be using the method of superposition. So if you take a look at the beam on the screen, we have a fixed support at point A and we have a roller support at point B. Then we have a distributed load of 2 kip per foot, and this is distributed throughout the span length of 18 feet, and we have a point load of 5 kip at point C. So this distance from B to C is 12 feet, and we have EI is constant. So this means that the material and property of the span length AB is the same with the material property of the span length BC. So now we are going to use method of superposition to calculate the support reactions. And we know that at point A we are going to have 3 unknown reactions. We are going to have an unknown reaction AY, we are going to have an unknown reaction AS, and we're going to have an unknown bending moment MA. Then at point B we are going to have an unknown vertical reaction BY. So these are the reactions we need to calculate. So when we want to use the method of superposition, we have to follow a series of steps. So the first step we are going to follow is we need to check the determinacy. So how do we check the determinacy? So basically, if we want to check the determinacy, we need to take a look at the number of equations and the number of reactions. And we know that the number of equilibrium equation is equal to 3, and the number of reactions. So how many reactions do we have here? As you can see, we have 4 unknown reactions. So meaning n arrow is equals to 4. So as you can see, if n arrow, that is the number of reaction, is greater than the number of equilibrium equation, meaning this is a statically indeterminate beam. So this is statically indeterminate. So as you can see, 4 minus 3 is going to give us 1. So meaning this beam is statically indeterminate to the first degree. So meaning this beam is statically indeterminate to the first degree. And this means we have 1 redundancy. So we have 1 redundancy. Because the number of reaction minus the number of equation of equilibrium, if we subtract this, we are going to get 1. So meaning we have 1 redundancy. So if we have the number of reaction as 5, and normally the number of equation is usually 3, then meaning we are going to have 2 redundancy. But in this case, we have 1 redundancy. So what does this mean? This basically means that in order for the beam to be statically determinate, we need to remove 1 support reaction. So this is what we are trying to say when we say this is an indeterminate, that is statically indeterminate to the first degree. Now the next step we need to follow is we now need to apply the method of superposition. So now we know that this beam is statically indeterminate and this is indeterminate to the first degree. So what we need to do is we need to take a look at the redundancy, and what we're going to do is we are going to try to remove 1 support reaction so that we can make this beam statically determinate. So you are going to choose where you want to remove the support reaction, but in this case I'm going to remove the support reaction at the roller support, that is at point B, because it is easier for me to remove the support reaction at point B, and it will be easier for me to solve other reactions if I remove the support reaction at point B. So now at point B, which is the roller support, so this is going to be the redundant. So now what I'm going to do is I'm going to split up my loads, and I'm also going to split up the redundant, such that when I add up those load and the redundant, I'm still going to arrive at my initial beam. So this is what we are going to do. So this is the next step. So the next step is to apply the method of superposition. So we're going to apply the method of superposition. So like I said, we are going to split up the load. So as you can see, the first load we have here is distributed load, 2 kip per foot, and the second load is 5 kip. So we're going to split this up. So the first one is going to look like this. So we're having the distributed load. So this distance is 18 feet. Then we are going to add this to the point load. So this load is 5 kip, and the distance from the feet support to the point B, this is 18 feet, while the distance from the point B to the point load, this is 12 feet. So now we are going to call this the loading structure. So I'm going to call this the loading structure. So now we also need to add the redundance. So because we are going to remove the support reaction at point B, so meaning this is going to be the redundant. So I'm going to say plus. So now we're going to have the feed support here. Then we're going to have the redundant by, and this is the support reaction by. So this is point C, and this is point A. So now this, we are going to call this the redundant structure. Redundant structure. So now this is what we have. Now the next step you need to take is you need to take a look at the redundant deflection. Now we know that we are going to be removing the roller support at point B, so meaning this is going to make it the redundant. Now if you take a look at the redundant, the vertical displacement is going to be equal to 0. The vertical displacement at point B is going to be equal to 0. So we know this, and this is at a distance of 18 feet. So meaning what we're going to say is we're going to say the displacement, so let's call this V, the displacement at the redundant, that is at point B, so we're going to call this VB, at a distance of 18 feet, this is going to be equal to 0. That is the vertical displacement is going to be equal to 0. So now we know this. We are just going to add up the displacement due to the load and the displacement due to the redundant. So we are going to say the displacement due to this distributed load plus the displacement due to the point load, then plus the displacement due to the redundant should be equals to 0, and these are at a distance of 18 feet each. So they should be equal to 0. If we can do that, we just need to calculate the support reaction By, then we can easily get the support reaction. So now if we have a distributed load acting on the beam, if we apply the load, it is going to try to deform the beam like this. So we need this displacement. So let's call this the displacement due to the distributed load. Then for the point load, it is going to deform like this. So we are going to call this the displacement dP due to the point load. Then for the redundant, it is going to deflect like this because the load is acting upward, so it's going to deflect like this. So this displacement, we are going to call this the displacement due to the redundant load. So now we just need to add up this displacement. So the first one, so the first one is the displacement due to the distributed load, and this is at a distance of 18 feet, then plus the displacement due to the point load, and this is at a distance of 18 feet, then plus the displacement due to the redundant load, and this is at a distance of 18 feet. So this should be equals to 0. So now we need to know the displacement due to the distributed load. We need to know the displacement due to the point load, and we need to know the displacement due to the redundant load. So what we're going to do is we are going to take a look at a table. So we need to take a look at the beam and deflection table in order for us to calculate the displacement. So for the first one, the displacement and due to this distributed load, if you take a look at the table, so now if you take a look at this table, we have a fixed support, that is, we have a cantilever beam, and we have a rectangular distributed load. So when we have such type of beam and such type of loading, the deflection or the displacement is going to be negative W L raised to the power of 4, then divided by 8, then multiply EI. So as you can see, because this load is acting downward, so meaning the displacement is negative. So that is why we have negative here. So meaning this is going to be the displacement for the rectangular distributed load. So it's going to be negative WL raised to the power of 4, then divided by 8 EI. So the displacement is negative WL raised to the power of 4, then divided by 8 EI. So this is for the triangular distributed load. Now for the point load, we also need to take a look at the beam deflection chart. So if you take a look at the beam deflection chart here, this is the type of beam we have and the type of loading. So as you can see, we are having a point load, and this is acting at the edge of the cantilever beam. So when we have such type of beam and such type of loading, the deflection is going to be negative PL raised to the power of 3, then divided by 3EI. And this negative is because the load is acting downward, so the displacement is going to be downward. So instead of positive here, it is going to be negative PL raised to the power of 3, then divided by 3EI. So the last one is going to be for the redundant load. So the redundant load is similar to the point load. As you can see, we have a cantilever beam and we have a point load. But for the redundant load, the load is acting upward. So meaning the displacement is going to be upward. And if the displacement is upward, so we are going to have a positive value instead of a negative value. So if the displacement is upward, we are going to have a positive displacement instead of a negative displacement. But the magnitude of the displacement is similar. So it is going to be positive. So instead of negative PL raised to the power of 3 divided 3EI, it's going to be positive PL raised to the power of 3 then divided by 3EI. So these are the displacements. So we just need to calculate this value. So this is basically equals to 0. So now for the first one, we have W. What is W? W is basically the distributed load. That is the rectangular distributed load. And the rectangular distributed load was 2 kip per foot. So this is going to be negative 2 kip then per foot. Then multiplied by the length. So what is the length? So basically the length is basically 18 feet. So this is 18 feet, then raised to the power of 4, then divided by 8EI, then negative, that is minus P. So P is going to be the load, that is the point and load. So this is negative 5 kip. Then multiply by the length. So what is the length? So the length is going to be 18 feet plus 12 feet, which is going to give us 30 feet. So this is multiplied by 30 feet, then raised to the power of 3, then divided by 3EI, then plus. Now this is going to be for the redundant load. So what is the value of P? That is the load. The load is basically the reaction BY. So this is going to be plus by, then multiply by the length L. What is L? L is going to be 18 feet. That is the distance from the feet support to the support reaction. So this is going to be 18 feet raised to the power of 3, then divided by 3ei, and this is equals to 0. So all you need to do, you just need to calculate these values. Go down. So if we use our calculator, negative 2 kip per foot, then multiply by 18 foot raised to the power of 4, then divide 8 ei. So what you need to know is that ei, they are going to cancel out because these values are constant. If you remember, we said ei is constant, so the ei are going to cancel out. So if we solve for this, the first value we are going to get is negative 26244 kip. So this is for the first value, that is for the distributed and load, then minus, so for the points and load, if you use your calculator, you're going to get negative 4500 kip. Then for the redundant and load, we are going to get plus 1944 by, then this is equals to 0. So now we can solve for by. So this negative 26244 kip minus 4500 kip, if you calculate this, we are going to get negative 71244, then plus 1944 by is equals to 0. So if you do the math, you're going to get by, that is if you divide negative 71244 by 1944, you're going to get by is equals to 36.7 kip. So this is the value of by. Now we know by, we can easily get other support and reaction by using equation of equilibrium. So we know by, and by is equals to 36.7 kip. So as you can see, we can easily get this reaction AY and the bending moment MA, because we know that AS is going to be equals to 0 because we don't have any horizontal force acting on the beam. So AS is automatically equals to 0. So we are left with just AY and the moment MA. So what we're going to do is we're just going to take the summation of all the forces in the vertical direction equals to 0 so that we can get AY. So summation of all the forces in the y direction is equals to 0, and we're going to assume all the forces starting upward is positive, while the forces starting downward is negative. And as you can see, for by, because we are having a positive value, meaning our assumption is correct and this force is indeed acting upward. So take note of that. So now for the other reactions, we are going to take summation of all the forces in the vertical direction is equals to 0. So we already know that by is equals to 36.7 kip, and this is acting upward, so meaning we are going to have a positive value. So this is 36.7 kip. So as you can see, we have a 5 kip and this is acting downward. Then we are also going to have another force, because we need to resolve this distributed load into its resultant. So if we want to do this, we just need to multiply the distributed load 2 kip per foot. Then we need to multiply this by the span and length. So it's going to be 2 kip per foot, then multiply by 18 foot. This is going to give us 36 foot, and this is going to be acting at the middle of this rectangle, because we are dealing with a rectangle. We are having a force of 36 kip. So now we have a downward force of 5 kip. This is going to be negative, and we also have a downward force of 36 kip. This is also going to be negative because they are acting downward. So it's going to be negative 5 kip, then minus 36 kip, then plus the force we want to calculate, and this is AY. So we're assuming this to be acting upward. So this is equals to 0. So all you need to do, you just need to use your calculator to get this value. So with your calculator, you're going to get AY is equals to 4.3 kip. So this is the value of AY. So as you can see, we are having a positive value. So meaning this is indeed acting upward. So now we know AY, we know BY. We just need to calculate for the moments at point A. So how can we calculate the moment at point A? What we're going to do is we're going to take the summation of moments at point A equals to 0. So I'm going to say summation of moments at point A is equals to 0. And we're going to say all the movement in the counterclockwise direction is positive, while all the movement in the clockwise direction should be negative. So if we apply a force of 5 kip, which relative to the point A, it is going to try to rotate this beam in the clockwise direction. So we're going to have a negative value, and the distance is going to be 30 feet. That is the distance from the force 5 kip to the fish support. It's going to be 30 feet. So it's going to be 5 kip multiplied by 30 feet. And this is negative because it is moving in the clockwise direction. So it's going to be negative 5 kip, then multiplied by 30 feet. And also, if we apply a force BY of 36.7 kip, if we apply this upward with relative to the fish support A, it is going to try to rotate this beam in the counterclockwise direction. So we're going to have a positive value, and the distance is 18 feet, as you can see. So it's going to be 36.7 kip multiplied by 18 feet. So we're having a positive value. Okay. So we're having 36.7 kip, then multiplied by the distance, which is 18 feet. Then also, as you can see, we're having a force of 36 kip acting downward. So if we apply this downward with relative to the fish support at point A, it's going to try to rotate the beam in the clockwise direction. So we're going to have a negative value, and the distance is basically going to be half of 18 feet, which is going to give us 9 feet. So it's going to be 36 kip then multiplied by 9 feet. So we're having a negative value because this is acting in the clockwise direction. So this is negative 36 kip then multiply by the distance, which is half of 18 feet, which is going to give us 9 feet. We also have the moments which we want to calculate, MA. So as you can see, we assume this to be in the counterclockwise direction, so meaning it is going to be a positive value, and AY is not going to produce any moments because this is acting at the point of interest, so it's not going to produce any moments. So we're having a positive value, and this is a positive moment, MA, and this is equals to 0. So all you need to do, you just need to calculate for MA. So you can use your calculator to get this value. If you do that, you're going to get MA is equal to negative 186.6 kip feet. Now, as you can see, we are having a negative value, meaning our assumption is wrong. Initially, we assume the moment is moving in the counterclockwise direction, but because we get a negative value, meaning the moment is in the clockwise direction. So this is moving in the clockwise direction instead of the counterclockwise direction. So these are the support reactions. So let me write this down here. AY is equals to 4.3 kip. BY is equals to 36.7 kip. Then the moment MA is equals to negative 18 186.6 kip feet, and we know that AS, the horizontal reaction, is equals to 0 because we don't have any horizontal force on the beam, so this is equals to 0 kip. So these are the support reactions on this beam, and this is how we can calculate the support reaction on a statically indeterminate beam using the method of superposition.